I'm Madan Muswati from Microsoft Research, and I'll be presenting two tools today. One is what we call for concurrency fuzzing. I'll explain what that is. And another one is to find data races in your program. So this is from Microsoft Research, and so what we have is like a cool technology. We're working on a tool, and so it's not as polished as you would see in other PDC presentations. But the whole point here is to actually put it out in front of you and get feedback so that we can do a better job when it actually comes out as a tool. So this is joint work with my colleague, Sebastian Burkhardt, who unfortunately was not able to make it today. So I will give the talk. And we also have a booth in the big room. So if you're interested in knowing more details, please drop by the booth as well. So the main problem that we are trying to solve is the problem of concurrency. If you're any serious developer at all, you probably have felt the problem developing, testing, debugging, and fixing bugs in your concurrent program. The main difficulty is that the executions are completely non-deterministic. The behavior depends on how the different threads interleave. And there might be some interleavings which have bugs. And unfortunately, those are the ones that you don't end up testing. And so when you ship the software, there are these like funky interleavings where there are bugs, and these bugs are very hard to find and debug. And they are called Heisenberg bugs because sometimes just observing the bugs make them go away, right? Because you add a printf statement that completely changes the way threads interleave. And so what was crashing once in 100 times, you add a printf, it doesn't crash anymore, right? So that's why it's called Heisenberg. And it's a huge productivity problem. And you probably know this a lot more than I do. People spend a lot of time just chasing even a single concurrency bug. So we're going to be seeing two tools, and both of them are trying to solve the problem from two different directions. The first is a tool called Cuz, standing for concurrency fuzzing. And you probably know about the term input fuzzing, where you take a program and then throw in some random inputs to crash the program. So concurrency fuzzing is a similar notion. What you do is you run your program and you randomly perturb the schedules. And this is something that current stress testing methodologies already do. You add a lot of random sleeps here. You throw a lot of lots of stuff and lots of noise in while you're testing. But what I'll show you is Cuz is actually a more disciplined way of doing it. And it works really like a push button tool. You can just attach it to your existing tests, and you just get more coverage automatically. And the second tool is called Featherlight. It's a data race detection tool. And so current tools for detecting data races, they add a lot of runtime overhead. And this tool is very lightweight. So the worst case overhead that we have had in practice is less than 50%. So what this means is you can actually have it on when you're doing your stress and functional testing. So first, let me talk about Cuz. So I'll start with a demo. So I'm going to take a program which is called Dryad. It's a fairly mature Microsoft software, and we actually found a bug in the software and actually demonstrate the bug. And so this looks like a typical scenario. You have a concurrent program, you write a lot of tests, and you run them. Things seems to be just fine. But they're not exactly fine. So if you run it a lot of times, there's actually a bug. So we did this experiment. We ran this program in a huge 8-way cluster with 8 machines and 8 cores. And we actually found that there was one failure in 200,000 odd runs. So the probability of finding a bug is very, very little, right? So let's see how we can find it. So I will demonstrate this program. So what I have is the Dryad program. And there's a test called simple channel test, which I'm going to run. See, I'll hit enter. It's doing some stuff. What it's doing is that it's actually, testing a part of the Dryad library. It's allocating some channels, doing some concurrent activity. So what it is doing is not important, but I just run it a couple of times. Everything seems to be fine. Just to make sure that I'll run it in a loop 100 times. And believe me, there is actually a bug in here. So you run it again and again, you don't seem to find a bug. Okay, and I've been extremely lucky if I actually found the bug when I run it 100 times like this, because this is like a 1 in a million bug, and I'm running it 100 times. The probability is actually very, very low. Now, what I would do is now attach cuz to this program. So let me let me. So I just want to say that so we can do better, and what we can do is to actually we'll attach cuz to the same test. And the important thing I want you to remember is that we can actually give mathematical guarantees that when you run the program with cuz, I can actually give you a probability saying that, okay, I'm going to find this bug with a probability 1 in 100, and I'll actually demonstrate that. So this is what you saw before. Now, cuz is actually a DLL, and I'm going to use a tool called detours that would inject the DLL into the test case. Okay, so what you saw happen was that win32cuz.dll here is our implementation of cuz for native programs. And it's a DLL, and you just inject it to your existing test case. And it's as simple as that. Right? You don't need to modify the code. You don't need to recompile it. We don't have to do any instrumentations. And you just have to inject this DLL. And what's going to happen is once you inject this DLL, every time the program runs, cuz takes control of all thread interleavings. Your OS and the hardware can do whatever it wants, but we will determine how the threads in your program interleave. And then we have like a fancy algorithm that will figure out how to find bugs in your programs with mathematical guarantees. So now again, I'm going to run it. It looks very much like running it before. One thing I want you to know is that just by attaching cuz, the program did not slow down. And but the probability of finding the bug is actually 1 in 10. So let me run it in a loop, and you can see what's going to happen. Right? So I just ran it a bunch of times and actually found some bug. Right? So at this point, you could say, hey, this could as well be a bug in cuz, right? Because it just got an access violation. But I want to actually look at this particular line here, and just to convince convince you that it's actually not a bug in cuz. You can see the program is accessing a very bad pointer. So there's a pointer that was actually freed, and the program, because of a race condition in your program, the program is actually accessing a bad pointer. And let me close it and then run the loop again. So you can see I'm actually running it 100 times. So the probability is 1 in 10. So roughly, you should see the program, the program to crash 10 times out of 100. Right? So this is not the behavior that you saw without cuz. Without cuz, the probability of the bug was 1 in a million or more. Right now, the probability is actually 1 in 10. Okay. So any questions about the demo?
Is that ratio from 1 in a million to 1 in 10 a property of this particular test? Or?
It's a property of this program. And so the probability that we can give you is depends on number of threads in your program and the number of synchronizations. I'll actually come to the talk to explain how we actually give the guarantee. But the one thing I want you to say is actually a mathematical guarantee. If you look at Las Vegas, the whole thing works around this probability that if you actually go to the slot machine, there's a probability that you'll actually win. And that means if you do it long enough, you're going to ultimately hit the jackpot. So in the same thing, in our case, if I give you a mathematical probability, you just run it a bunch of times, you're guaranteed at least mathematically, that you will hit the bug. So that was the demo. So this is sort of the main punchline, is that instead of doing stress testing, you're better off injecting cuz and running your same test with your existing test framework, and we just immediately like magnify the probability that you find your bug. So for this experiment, so this is actually, since in my laptop, the probability is 1 in 10. In the server, it is actually 1 in 4%. And so that's why this slide is actually showing you like 4% as opposed to 10%. And so even with this 4%, we actually 3 days of stress testing is equivalent to like 33 seconds of cuz testing. And that's the improvement we can give with cuz. So now I'll actually explain how cuz works. And it's going to be a little bit mathematical, but it's not something very hard. Okay? So the main problem is that programs have astronomically large number of schedules. And any one of them can be buggy. And that's why it's very hard to find. And typically, when you're testing, you have finite amount of resources to test, because you want to ship your software within a month or so. And so you're not going to have the resources to make sure that every interleaving is correct. Okay? So what's the best you can do? So the problem we tried to solve was this. So let's say you had resources to just run the program once. What's the best you can do? The best you can do is to try to maximize the chance that you actually find the bug. So we want to maximize the probability of finding a bug in every run. Okay? So this problem turns out to be really hard, and I explained this with a little game. Okay? So what happens is I gave you a program. It has n threads, and it executes k steps. And to a first order of approximation, it has around n to the k possible behavior. Right? From the initial state, you can execute any one of the n threads. From each of those states, you can execute any one of the n threads. So you have a branching factor of n up to depth k, and you have n to the k schedule. So let's say you're playing this game with an adversary. Right? So you have an algorithm to say, I'm going to explore one of the schedules, and the adversary picks, OK, which one of the schedules is going to be buggy. So first thing you should realize is that no deterministic algorithm is going to work. Right? So because what happens is the adversary knows your algorithm. So if he knows that you're going to be executing this interleaving, then the adversary can say, I'm going to select this to be the bug. Right? And so probability you find this bug is actually 0. So though your best bet is actually to have a randomized algorithm. But even if you have a randomized algorithm, since the adversary can pick any one, the probability of you winning is actually 1 in n to the k, which is actually very, very low number. Okay. And so the main insight is that real bugs are not this adversarial. And if you look at the way people do current stress testing, where you try to randomize, you have this problem. And that's why you're not doing as well in finding the bugs with existing stress testing methodologies. Okay? So the main insight is that bugs typically require few things to go wrong. And if there is one schedule that finds a bug, there are probably like many schedules that find the bug. And so your algorithm has to somehow make use of this fact. Okay? So let's look at some bugs to see how we can use this. Okay? So here is like a classic ordering violation. This thread actually creates a thread called child, and then initializes this memory P. It actually should have done it the other way around, because there's a race condition now that while the child is dereferencing this, right? While the parent is allocating this memory, the child could dereference, and there can be a bug, right? And so if you look at how the scheduler can force this bug, it needs to make sure that it gets one thing right, right? So it actually needs to schedule this instruction before this instruction. So it just needs that one constraint, and then you find the bug. Right? And so let's say if you're playing the game with the adversary, in order to find this bug, you just need to get lucky enough to get this ordering constraint right. It doesn't matter what you do before or after. So similarly, let's look at this atomicity violation, where you do the initialization correctly, but the child is setting P to null, and you are checking if P is not null and then dereferencing. Now, this is a bug because if I execute this instruction between these two, then this dereference can be buggy. Right? So, but in order to find this bug, you actually need to get two things right. You have to make sure that you schedule this before this, and then this before that, right? So in the sense, so you need to satisfy two ordering constraints to find the bug. And let's look at this classic deadlock example in which two threads are acquiring locks in different order. How many constraints do we need to get it right? You need to make sure that the parent acquires the lock A before the child. That's one constraint. And the second constraint is child should acquire lock B before parent. And so again, so the whole idea is that real bugs, they're not very complicated. They require like few of these constraints to get right. And somehow we have to utilize this fact. And so I'll skip a lot of math here. But essentially what we have done is defined a notion of a depth of a bug, which is the number of ordering constraints that you need to find the bug. And I'm going to make a hypothesis saying that most bugs in practice have a depth 1 or 2. What we have empirically evaluated is that there are lots of bugs in practice that are of depth 1 and 2. And so if I'm able to find all bugs of depth 1 and 2 in your software, I think, and all of the software that we ever ship, then I think the world would be a much better place. Right? So we're just going to be focusing on bugs of depth 1 and 2. And now the game is slightly modified. So now what happens is that you have an algorithm, and then you also pick a depth D. So the adversary cannot pick any arbitrary bug. He can pick any bug of a particular depth. And then this is actually very crucial. So once you fix this depth, then it turns out that you can come up with a strategy, which is what Cuz does, to find the bug with this probability of 1 over nk to the d minus 1. It looks like a very complicated formula, but I'll explain with examples. For example, let's look at this ordering violation. D is 1. And if you evaluate that formula for d equals 1, it becomes probability of finding the bug is 1 in n. So if your program forks 10 threads, then the probability that I find all ordering violations is 1 in 10. That's as easy as it is with Cuz. Now, for atomicity violation, it gets a little bit harder because it's a bug of depth 2. The probability of finding this bug is 1 in nk. So n is approximately tens, and k probably gets around millions for your tests. Right? So this is like 1 in a million already. Now, you might say, hey, 1 in a million is actually very low. But think about it. Let's say you have 1,000 machines, and each of them can run 1,000 runs of Cuz. You're guaranteed to find this bug. Right? And 1 in a actually a lower bound. That means this is the hardest atomicity violation or a hardest bug of depth 2 that you can introduce in your program. And regular bugs are actually much easier to find than this. And that's what we have found in practice as well. And so in our experience, same thing with deadlock 2, 1 in n to the k. I mean, this is also like, we can find this bug with the probability 1 over nk. We have applied this Cuz tool to many programs at Microsoft, and we have been very effective. Many of the times you just attach Cuz and we crash programs in the first few runs. So I believe this is a very effective fuzzing tool. And once you're using Cuz, you don't have to do any other randomization technique, like inserting noise, random sleeps, trying to change priority mechanisms. You don't need to do all of that. And so the nice thing with using this disciplined mathematical algorithm is that your resource usage is very, very good. You don't need to run your stress tests on these huge server farms. We just need one core for one run of Cuz. And so that's how effective we are at utilizing our resources. And people usually don't have this notion of a probabilistic guarantee when you're doing your tests. Right? You just leave it to God, right? Say, OK, I'm just going to do as much as possible and see what happens. And I think one of the things that we are trying to do in research is to see if we can actually improve testing mathematically. So let's say we do have a testing algorithm that gives you a probability. OK, here's a bug. I can find this with the probability 1 in a million. Then you can start playing games like, OK, the cost of a bug is $1 million. The cost it takes to test this program, one run of a program is a cent. Now, it can actually start doing the math to say, am I better off shipping the software with the bug or should I use the resources to do testing? So it's actually very, very important to have this probabilistic guarantees. And the tool is a prototype. We're working hard on a release. So please give us feedback. And that will, the more feedback you give, the faster we'll get to the release. Right? So let me check my time. Yeah, so the second part of the tool, so by the way, before I go to the next part, do you have any questions on CUS? Yeah. Oh, OK, so the question was, how does CUS relate to chess? So we presented chess last year. So these are two tools from the same team. So you can think of CUS as an evolution of chess. So when we developed chess, we were focusing on unit testing. So we thought, just as you can unit test your sequential programs, you can unit test your concurrent programs, and chess was tuned towards that scenario. And last PDC, we got a lot of feedback. And so all of you, almost all of you said, hey, we don't have unit tests for concurrent programs. So it'll be nice to write those unit tests, but it'll be nice if you can actually give us better coverage for existing stress tests. So if you think about it that way, CUS was actually your idea, right? So so we essentially designed CUS for the the stress testing and the functional testing scenarios. So the algorithms, so some of the the techniques we use in controlling the schedules is common between both chess and CUS, but the algorithms are different, and because they are tuned to different scenarios. Yeah.
Does CUS schedule interleavings across the entire system or just your application?
So the question is, at what level does the CUS control the interleaving? It's currently per process. So you attach it to a process, then it controls the interleaving of any thread that is created by that process. Now, if you're doing a multi-process scenario, then you can attach CUS to each of the processes, and then it would just work. So we are not controlling. So you have to tell explicitly which processes you want CUS to control. And so one of the things that we have found is that CUS is finding a lot of bugs, and people don't want to do that. So let me explain. So in the sense, there is a tester who's responsible for model A, and then he runs CUS on it, and then he actually finds a race condition because of module B, right? He doesn't own model B. Now, it'll be nice if there's a way to focus CUS to just one module, so that we just control the interleaving of one module. That's something that we are currently working on. So we can give more fine-grained control within a process. That's harder, but we cannot do that right now. Yeah. Question.
Does CUS control interleavings only with respect to window synchronization primitives, like just the standard set of synchronization primitives? Is that the level at which it operates?
So currently, we have implemented the Win32 CUS controls only Win32 synchronizations. So if you want to implement CUS in a different layer, then you need CUS for that layer. So for example, if you want to do it for managed programs, we need managed CUS. If you want to do it for Azure programs, you need an Azure CUS, right? So it's actually tied to a particular API. And so one of the things, again, this is good feedback. So we are trying to make it easier to extend CUS and chess to different APIs. So currently, we just support it for Win32, right? So. Oh, yeah, so CUS does give you much better repro, but we do not guarantee repro. So we control thread interleaving. So our thread interleavings are deterministic, but there might be other noise in the system, right? Let's say your OS changes something, you do a system call like.
Natural fuzz will defeat the probability of.
Right, so the mathematical probability I said was without those noise, right? But so let's say there is an extraneous noise in the OS, right? Whenever you call a file system call and then it returns null with the probability 0.1, and if it's null, that it triggers an race condition, right? So then you have to multiply the two probabilities, right? So we do give repro modulo external non-determinism. So randomized algorithm is based on a random seed. So you run cuz with the same random seed, and if there's no external noise, you actually do get a repro.
So in your example, if you recorded that seed with all the failures,
Yes, we do that, yeah.
then you'd get much better than even the last run you did.
Yes, so what I did not show the repro. So what happened by default, cuz when you start, it uses the time as a random seed. We log that into a file. So there's a way to tell cuz, OK, use that particular random seed, then you would get repro. Yeah, so question? Yeah.
Playing around with these priorities, does it expect the performance levels, high priority, low priority, the priority levels?
Yes. So the question is, like, how does the mucking around, schedule mucking around that we do play around with other mechanisms that the OS has? We actually honor all of that. So the way you should think about cuz is that it sort of adds random delays to your threads. So whenever you do a synchronization, our algorithm determines how long to delay this particular thread. So it's like taking your program, inserting random sleeps, but we insert the random sleeps in an intelligent way. And everything else is the same, right? Yeah.
Wondering how cuz operates on a multi-core system. Does it collapse everything to a single core, or does it collapse the threads in parallel?
It does not run threads in parallel. That's because we want perfect control over interleaving. So if there are two threads running concurrently in the hardware decides how the threads interleave. We don't want to do that. And so what this means is that we are running one thread at a time, but we are not squishing them to the single processor because we don't want to change the thread affinity in your program. So the threads are running on multiprocessors, but cuz orchestrates them in such a way that there's only one thing which is running at a time. So you do lose some parallelism when you run with cuz, but what that means is that you just run, if you have an 8-core machine, you run 8 versions of your program, and then you get some of the parallelism back.
Some bugs are just big slowdowns because of dogfighting between threads for resources.
Yes.
Help isolate that. Can we mix with profile?
Very good question. Does cuz find performance bugs? Is that some of the performance bugs we do find, but the tool is not designed to look for performance bugs per se. It's more for these assertions or race conditions, a safety violation. You can run with profiling, but one thing that you have to be careful with is that our whole job is to actually slow down your program, like to force different race conditions. And so, so one of the things you have to be careful is like if you find a bug, is it because of something that we introduced, or is it something possible? So I think there is some engineering to make sure that we do not artificially introduce performance bugs. But that's something that cuz cannot handle currently. Good questions. Yeah. Mm-hmm. Yes. OK, so another good question. So let's say you're using like another threading library, like Intel thread building blocks or TPL. And then cuz would actually see the threads that the threading library schedules the different tasks on. And then what you need is that you actually need a cuz for that library. So instead of building cuz for Win32, you need a cuz for the thread building blocks. So cuz needs to know what your tasks are and how they interact, what are the synchronizations between the tasks. And then we can actually do it at the thread building block level or the TPL level, right? No such version is available right now. Yeah. So all that, so again, this is like a technique. And you can apply this technique in a lot of tools. And currently, we are supporting only for Win32. Right? Mm-hmm.
So curious what kind of granularity of forecast. For example, say you had a race condition where you're doing 64-bit move, and you had that's on Win32, so it's not part of the convex, and you had the reading for one of the 30-bit.
Right. So OK. So what interleaving granularity that cuz can do the interleaving at? So if for example, if you don't give me a way to instrument your binaries, there's nothing I can do, because what you want to do is that there is an atomic instruction. There's an instruction that moves 64 bits, and in the hardware it's actually implemented as 2 moves, and so you want to schedule another instruction between the 2. From pure software level, I cannot do it. But what I can do is to actually instrument your program. So look at your instructions and say, oh, whenever I see a 64-bit move, I actually split that into 2 32-bit move instructions, and then Cuz can actually do the interleaving at that point. So we actually, internally, we do have a binary instrumentation tool called Vulkan that we use to look at all these non-atomic x86 instructions and actually insert a Cuz point between the 2 so that we can find those bugs. And that's actually a very fruitful place to find a lot of bugs. Yeah. Question? Mm-hmm. Could you repeat the question?
According to your experience, for how big project is the tool practical?
So one of the things that we have designed Cuz for is to attach it to any program that runs. I mean, that's our ambition. So currently, we can run it on large servers. We have applied it to many server code at Microsoft. So it depends on how we write the test. So we are like a randomized schedule. It's like, so the best way to think about Cuz is that you take your test, run it on your OS, and then OS and the hardware determine how the threads interleave. You can do the same thing by running it on Cuz, and then Cuz determines how the threads interleave. So if you can run it on the OS, with some amount of engineering, you should be able to run it on Cuz. So there are no time limits. You can just take your existing stress test, run it on Cuz. Yeah. Mm-hmm. Yeah. Question.
Yes, do you plan to extend it at some point to support things like cross-process synchronization?
Yes, so we have plans in the future, but that's coming in future. So what you want to do is you want to orchestrate the threads across multiple processes so that you can force race conditions. That's been a big request from our customers, like product teams who are using Cuz. Yes, so that's actually in our pipeline. Yes. Exactly. Yeah, and that. I mean, a lot of people have told me that that's another fruitful place to look for bugs as well. Yeah. Mm-hmm. Anybody else had a question? Yeah. Yes. So Cuz is a scheduler. It doesn't know what is right and what is wrong. It's up to you, like the test, to figure out what is right and wrong. For example, if you make an access violation, that's obviously wrong. But you might actually have race conditions that produce a wrong test output. We would have no way to find that bug because that is so application specific, right? So we expect the tester to actually write the right oracle. Yeah, that's any assertion failure, any deadlock, any live lock, and then any data race, access violation, all those things we can find, right? So if you can find that bug by running stress, you can find the same bug with Cuz. Mm-hmm.
So are you planning to interface with the UMS scheduling on Win 7 to actually do Cuz stuff across processes?
UMS.
Because it will allow you to write your own machine-wide scheduler, right?
That we have thought about using UMS within a process, but not for multiple processes. But that's a good idea. So you could use UMS for machine-wide scheduling as well. Yeah. Yeah. So yeah, that seems like a good idea. Yes, we should try that. Yeah. Okay. So maybe I should go to the next. But I can still take more questions if you want. So come to the booth if you have more questions. So the second tool I'm going to present is called Featherlight. And everybody here probably knows what a data race is. It is like a special class of race conditions where you're accessing data without proper synchronization. And it's a good place to look for concurrency bugs. And the one problem is that there are data race detection tools that are present, but they actually add a lot of overhead. And many people don't use it because once you slow down your program, your tests start breaking because I expected this thing to finish within 10 seconds. Now you run your data race detector, it takes 100 seconds. And so your test failed for wrong reasons. And so there's a lot of problems because of the overhead. And so one of the things that we designed Featherlight was to actually reduce the runtime overhead. And it's very, very low, like 0 to 10% most of the time. But there are programs for which we slow down by 50%. And the main idea is that we actually want people to use data race detection when you're doing your functional and stress testing. So let me explain what a data race is. So here's a program that you have thread 1 that acquires a lock and does, checks if P is not null and then dereferences the pointer P and then releases the lock. Now this is the bad thread. It is actually setting null and it's doing that without acquiring the lock, right? And so there is actually a conflict between these two accesses. And so if this happens between these two, then you can actually, this data race can result in a bug. Now, let's see. So the actual definition is that if you have two accesses in two different threads and they conflict. So by conflict, I mean that at least one of them, so they both access the same memory location and at least one of them is a write. And if these two accesses can happen simultaneously, that means that there are two processors and one is about to schedule the read, another one is about to do the write to the same memory location, that is a data race. And so typical dynamic data race detection work like this. You take a program and then do the instrumentation. And what the instrumentation does is that on a particular input, when the program runs, we actually collect data about the program. We collect all the synchronizations that the program performs and all the data accesses. And then you feed it to an algorithm. The main overhead comes because collecting data accesses is actually very, very reduces the program. Adds a lot of overhead to your program. Like a typical program does a memory access 1 in 5 instructions, rough back of the envelope calculation. And so you have to 1 in 5 instructions. You have to log something, like make a function call, log it, and check for data races, and then get back and do the access. That slows down a lot. And so this is the main reason why you actually have a lot of overhead. And the main idea is that, hey, maybe we don't have to find all data races. If you either have a data race detection tool that is perfect that nobody uses, or something that is less perfect but something that everybody uses, we probably will find a lot more bugs. So that's a basic idea, is that instead of logging all data accesses, you actually have a sampling algorithm. And this sampling algorithm looks small in this picture, but it's actually a lot. It's very difficult to come up with a good sampling algorithm because data races involve finding a conflict between two. And so when you're using sampling, you have to make sure that you sample both. So if you randomly sample, then the probability that you actually find the data race becomes very, very low, right? If you have like 1% chance of sampling this, 1% chance of sampling this, the probability that you sample both is 1 in 10,000. So you need to be a little bit much smarter in sampling. And the basic idea is that data races happen in paths that do not execute often. So that actually works for us, because what you need to do is that if there's a path that executes very rarely, you instrument it with 100% probability. If it's something that is executing really, a lot of times, you instrument it with a very, very low probability. And so that works for a performance argument, because it's OK to slow down your cold path perfectly fine. You just want to get away from these fast paths. And so that's a basic idea. And we have evaluated this algorithm, and then we are able to find around 70% of the data races by simply sampling less than 2% of the memory accesses. So we are not perfect. We don't find 100% of the data races, but what you get is that you just need to sample 2% of the memory accesses. And so, like, for example, interactive applications like IE, you hardly see the difference. You just run it with Featherlight. There's no difference. But if your program is doing lots of synchronizations, then we actually have a slightly higher overhead. And let me see if I have a time for a demo. I can go till 1:30, right? 12, no, actually, I have only 5 more minutes. OK. So maybe I'll just do a quick demo here, just to show that the tool is working. So we call it F-Light for Featherlight. And so let's see. Wow. Slim manner. So this is a program. You can see that it does some concurrent stuff. It doesn't print out anything. And the way you run Featherlight is just to just say, OK, just do flight.exe before your executable. And now Featherlight runs. And then you can see that it actually reported 3 races. I just forgot to mention that Featherlight, we do support both native and managed code. And our instrumentation, so we are planning to actually release the managed version of Featherlight very soon. The native version will come later because instrumenting x86 code is a little bit harder. So just by running, you can see that we actually found 3 races. And once you have found a race, we can actually do /trace. So if you run your program, you don't find any race, then it's pretty fast. Now, the second level is that now that you know that there are races in your program, then you can actually give a trace option where we do a little bit more work and we actually log, like give you the PC value of the 2 accesses so that you can debug it. And then, so now it's a little bit slower, but then we can actually have a nice, like a viewer to actually show you the different data races. Okay, and this is, let's see, let me show. So this is what happens is that on this side, this is the history of what all happened, the different synchronizations and data accesses your program did. And then these are the, the code for 4, there are 4 threads in this application. So if you have like a dual monitor, you can actually see 8 threads very nicely in this GUI. And I don't think it's visible in this monitor. So these 2 threads are actually, these 2 accesses are actually marked red. Those are the ones that participate in the data race. You can see it's a thread 2 and thread 3. So I'm just going to remove, I'm just going to focus on those 2 threads. So you can actually click on this to say, OK, so the thread 3 is actually doing this interlock, compare, and exchange, while this thread is doing this read. And so that is your data race. So this is how much we can actually get you to the point of the data race. There is one thread which is doing an interlock, compare, exchange. And so it is a synchronization variable, but this guy is doing a read without doing any synchronization. That is a data race. So that ends my demo. So let me go back to my presentation. I think that is my last slide. Yes? And so do you have any questions on Featherlight or on Cuz? Yeah? Mm-hmm.
What is different from VQ which Intel provides?
Pardon?
What is different from VQ which Intel provides for data?
So yes, so there are lots of data race reduction engines. So we actually have a sampling algorithm that reduces the overhead. So that is a big difference. Yeah. And so any more questions? So for the rest of the PDC, I will actually be in the big room. We have a demo for Cuz. So drop by. You can actually try out the demo yourself. If you have any more questions, feel free to drop by. And I can also demo Featherlight there in the demo as well, in the booth. Right. OK, thanks. Thanks a lot for coming.